Okay, so this is the sort of introductory technical talk for PyPy, as opposed to the advanced technical talk for PyPy, which is going to be after lunch. And as we say, I'm just trying to be reasonably basic and talk about what we've actually achieved, and not talk about how we're going to take over the world and why you'll all be using PyPy by December 2006 or something. So, obvious question, indeed, it was the first slide on the last talk. What is PyPy? Number one, it's an implementation of Python written in Python. Number two, you could use the word PyPy to describe the open source project that is implementing this implementation of Python. Answer number three is this is a specific targeted research project, which is a piece of EU jargon, which is partially, as Holger explained, funded by the EU. It's about 60% of the funding comes from the EU, I think. Right, a demo. So, the product of the process, which I'm going to describe in the next 10 minutes or something, is this executable called PyPy-C. As you can see, it looks rather like C Python. You can do C Python-y type things, such as import sys. I've lost the point again. So you can see which modules are in the, which names are in the sys module, print things, define functions. You'll notice that it has 4 angle brackets for the prompt. This is mainly so we don't go insane trying to remember whether we're running PyPy-C or PyPy at any given time. Yes, so I have to say it's fairly slow. It runs around the same speed as C Python, as Python. Depending on what you're doing, it's from 3 or 4 times to 10 times as slow as C Python at the moment. We can make binaries that do things that C Python cannot do easily, like stackless, coroutine type features, Greenlets built in without scary assembly hacks, and with this thing called thunk object space, which allows a form of lazy evaluation, and which is more of a demo than anything else, because a lazy evaluation combined with a language which permits side effects is not a way to stay sane. This talk is mainly about what we've done to get to this point. So, PyPy, from a code point of view, has 2 main parts. It has the standard interpreter, which is a piece of PyPy jargon by now, which means the code that does essentially what C Python does. It takes bytecode, it evaluates it. That's more or less it. We have the analysis toolchain, which takes the standard interpreter and compiles it to analyzes it and compiles it to C or LLVM bytecode. We have some other stuff as well that we've generated as we need. You could put the PyTest library in this, so that's being a bit mean to PyTest, I guess. The standard interpreter is written in a mostly static subset of Python, which is dubbed RPython, another piece of project jargon. This means that it runs on C Python too, which is important because that's how we unit test our standard interpreter, is by running small parts of it. So yes, as C Python does, it has a parser and compiler, a bytecode evaluator or interpreter, and the standard object space, which is on a few slides. What is RPython? As I said, it's a restricted subset of Python that is static enough for an analysis toolchain to cope with, which isn't much for a definition, but you kind of get used to it. It is Python, so it's a subset of Python, so we can run it on top of C Python. Yeah, so the 2 parts of the standard interpreter are the bytecode interpreter, which doesn't claim any knowledge of the objects it's manipulating. If you're just adding 2 things, you take 2 black boxes, you add the black box, and you get the black boxes, and you get another one. This means that we can use a completely different implementation of objects, ones which in fact contain no values at all, which we use to compute control flow. The standard object space, which was referred to on a few slides before, implements objects that look exactly like CPython, so it's very nearly exactly like CPython. The parser and compiler are based on code that's been lying around in the Python community for a while. Jonathan David Reel wrote a parser in Python for Python, and CPython has contained a compiler package, which unfortunately contains some bugs to do with scope resolution and nasty things. And these were converted to RPython so they could be translated and have been incorporated in the project for some time now. There is work currently going on to allow runtime manipulation of the grammar. This is one of the research aspects of the project. So that's the standard interpreter. It works. It's being extended in some directions, but it's been around for a while now. The analysis toolchain is generally more recent. It has 4 parts, roughly speaking. The flow object space, which does control flow analysis. The annotator, which deduces information about these control flow graphs. The R-typer, which is hard to explain. And the low-level backends, which cover C generation. So, the flow object space is, technically speaking, an abstract domain for the bytecode interpreter, which is computer science jargon as opposed to PyPy jargon. It implements objects as either constants, which is objects that existed before the analysis started, or variables. It works on one control object at a time. The outcome is a control flow graph, and it's been around for over a year, and it basically works, and we don't have to think about how it works anymore. The RPython annotator, it works on an entire program, which is, as opposed to the flow object space, which works on a function, essentially. And yeah, it deduces things about what might happen at runtime. So a particular example of this is what type a variable will hold, though that's not a particularly good definition of what it does. Yes, the annotator works in an interesting way, but there's a fantastic paper on the website which describes how it works. So if you want to know, you should go and read this paper called Compiling Dynamic Language Implementation. Great. And the annotator was one of the later pieces of the puzzle. It's been working for 6 to 8 months or so, and it doesn't get worked on very much anymore. It gets refactored occasionally and extended to cope with new situations, but it basically works. Right, the R-typer. The job the R-typer does is it converts the high-level output of the annotator. The annotator produces information which says, we're adding these 2 variables, and we know that they're integers. The R-typer converts this to an operation that says, add these 2 integers, which perhaps doesn't seem very deep, but in more complicated examples becomes very useful. I guess you could say it makes decisions about the memory layouts of the objects when you run the translated program. That's its main job. So the R-typer was the last piece of the puzzle really before we could run a generator working with PyPy-C. So it was something like August 2005. And it's a very active area of development. Lots of work is happening at the R-type level now. The low-level backends, they take the low-level operations produced by the R-typer and write out C code or LLVM code or, astonishingly, JavaScript code. And they work. It's kind of an annoying job, which perhaps isn't that surprising. You have to do lots of stuff with strings to make sure that the types appear in the right place in the program. We've had a C backend essentially forever, but it keeps getting changed. Basically, a theme of the last year or so is to do less work when you're generating C source and more work before then in the R-typer. To describe the project from an open source point of view, well, it's an open source project. We use the MIT license, which was decided in about 3 seconds in a pub in Hildesheim. There's about 10 people working on PyPy full time. It's a very distributed project. We live in 6, I think, or maybe even 7 countries, and there are part-time contributors who live in many more. We try and be a welcoming project. I mean, subscribe to the mailing list, come to the PyPy IRC channel, talk, ask questions. We'll try and answer them. So the sort of things we're doing right now, which I don't want to talk about in much detail because they're not really done yet, we're writing a just-in-time compiler. There's integration of logic programming, constraint solving, and data flow variables into the Python language. We're modularizing the garbage collection. We want to be able to experiment with different garbage collection strategies without having any impact on the rest of the source code. And there's all, of course, just general refactoring, as I said before. There's a trend is being to do less and less at source generation time and more at R-typing time.
So I would like to continue the talk, going a little bit more into details which I was involved in the last time. As we have seen, the PyPy project is quite large and it's aiming at a different set of tools at the same time, different set of targets at the same time. It is not trying to be a replacement or something else than CPython or other IronPython might be. It tries to give you options to configure your target, what you want to have. For instance, at the moment, what we have are different approaches to garbage collection. You can have reference counting. You can produce a binary that uses the Böhm collector, and there are going to be other collectors as well. At the moment, we only have those. Then there is an option to have stackless support, for instance. That means you can have the stackless extension included into PyPy without rewriting any line of code. It's just built into the code generator to be able to produce stackless support code. Other things are other object spaces which have different behavior, like the func object space or doing lazy evaluation. Other options to configure are what kind of backend do you want to use? Do you want to produce a C source from PyPy, or use LLVM, or even the new JavaScript backend? There are more backends to come. So this is all optional, configurable, and it's all one source code that can be tailored by options. Well, what I'm talking about is variations on an old theme. I've been working on Stackless Python since 1999 now, and it went through a lot of redesigns, and the largest redesign ever was the integration into PyPy, because at that time I learned what the basic nuts and bolts are, and what you really need, and other things are just dealing with problems of the language. So the idea of Stackless Python on top of PyPy is to start from scratch with a minimalistic code base, only using tiny coroutines. And these coroutines are supported in the internal layer, named the interpreter level, and they are also exported to the application level. Interpreter level means we can use the coroutine objects to implement high-speed protocols for sockets, for instance. This can all be thought as like built into the C language, but the C language in this context is our R-Python language, which replaces C. So we have some low-level support for being parallel, but this is also exposed to the application level and comes in different flavors which can cooperate with each other. So the base implementation is very minimalistic. Expose these high-speed coroutines to the R-Python developer who can use it to build other libraries. And also, since there has been some development over the years, meanwhile there are not only the tasklets, which some people might know from Stackless Python, there's also the Greenlet implementation, which was developed in parallel by Armin Rigo, and it has a slightly different interface, has different target of users, and actually all these concepts can be merged into one, and they can be supported by one simple basic coroutine switching interface, and they can live with each other without interference. So you can have coroutines, tasklets, greenlets, or other structures at the same time, and they will switch and they will not interfere with each other, and they will not slow down each other because they simply don't see each other. So what is a coroutine? A coroutine is some point you can switch into a certain context and you can leave another context. In coroutines this is done explicitly, which is a bit clumsy because you have to keep track of which coroutines you have. This was much easier with the Stackless approach, where we simply had an anonymous list of objects which could be switched to each other. But the intent of the coroutines is to be the minimum possible approach, and everything else is built on top of that. Well, actually, switching from one coroutine context to another one is updating the so-called current coroutine. The current coroutine is always what your own running program is at the moment. So when we start a Python session, PyPy session, and we do nothing at all, but we are actually then running the current coroutine. Switching to another coroutine means we have some other coroutine waiting to be executed. We wrap up the current one into a structure which we store somewhere, and we give the context and continue computation in the other coroutine. This is not preemptive. This is very quickly done because it has only a very tiny footprint to carry around. And it is extensible by other concepts. So internally, I started with a class hierarchy, building the internal coroutines as a basis implementation. Then these coroutines are only exposed to the internal level and not meant to be used in applications. For applications, we have the application coroutine, which is just a thin wrapper around this implementation. On top of that, we have the tasklets and the greenlets, which all share the basic switching capabilities, but they have a different interface and different users in mind. So actually, there's no hierarchy at all. They appear to be disjoint and not disturbing each other. So there's a very simple API. This is actually the API that's exposed to the Python level on application for applications. The internal layer is just a little bit simpler. We just have create a coroutine, bind it to some function with some arguments, switch to it. This is the basic operations which are possible. Then there are some additions like checking whether the coroutine is still a valid switch target or if it has run out already. Then we can raise an exception into it and say we want to kill it. And we can ask the system to give us the current coroutine, which makes sense if you don't want to spell the specific target, but just find out what is running actually. So everything else can be put on top of that. Well, coexistence of these concepts, it wasn't very clear for me from the beginning, but after a short while it turned out that it's really simple to think in terms of there is always, for one concept of implementing coroutines or tasklets or something else, you maintain one global state variable that tracks your current coroutine. And by doing that, you are creating a distinction between different switching concepts. So they actually don't see each other and don't know that there's something else switching. A coroutine is exactly running as long as it is the current of some state variable. When we exchange the state variable, something else is running in the context of this current principle. So they do not interfere with each other. Well, this is a very extremely compact implementation compared to stuff I did with Stackless before. This is mainly because the support of PyPy is so big. PyPy generates the necessary calling conventions which are needed to make this implementation so simple. It's very short. The the generated code that we produce in the Stackless case is slightly different from normal C functions, since it has some extra state variables carried around. So the functions we are calling are able to unwind the C stack while they are running, so they can be stopped, moved away into some structure, and restarted at a later time. So this is, if you look into the produced C code, it looks quite unreadable because it jumps in and out of functions all the time. But we don't see that from the Python level, and it's very convenient to work with this support. So in comparison to the Stackless Python talk we heard in the morning, this approach does not need any compromises. There are no stack tricks at the moment. We don't fiddle with the C stack at all because we have the completely supportive code implementation. This will probably change at some point when we are calling back into external library where we have no control about. Then this same kind of problems like are we able to switch in a cooperative manner, or do we have to do some stack hijacking? This will come up again, but I hope we can use the same nice interface as we did in this case and put that in the backend as well. So what's the future? I don't know. I hope this is the future of Stackless Python. My way to get rid of it, in the sense of put it into PyPy and have it maintained for the rest of the time. Actually, I have to work on the C Python implementation as well, because PyPy is not ready enough to say this is all. So I would like to take the chance to invite everybody who is interested to join in a sprint on porting Stackless Python. Will be in the next 4 days, and I will try to help with that. Thank you very much.
I was just curious, what was the EU's main interest in funding PyPy?
Well, I think it was a challenge for them to fund an open source project, which had never been done before. So it was a challenge for both us and them. I think they liked the idea. It was interesting and new, and we promised a lot. And as I heard back, they were quite astonished how much of the goals we had on our payroll we actually achieved already. So we seem to be quite successful.
You mentioned being able to generate JavaScript code. Is this sort of the step forward from Ajax to Apex or something?
Well, JavaScript is one example where we try to adapt to a higher level interface. What we've done with C and LLVM is very low level because we are attaching to on the byte level essentially. If we try to connect to higher level backends like JavaScript is one example. Squeak will probably be supported very in the near future, and other things like Lisp, for instance. They would benefit from an interface where we attach to a higher level, where we don't go down to the byte level, but really use existing structures in the implementation. And this is the first step towards that. So it was a toy thing, but actually it turns out to make sense, because you would be able to run your Python script on top of your JavaScript in the browser.
Is there any plan to target JVM or the CL output backend? And can you explain what the LLVM is?
Yes. Okay. Yes, to the first part. Though possibly not terribly soon. I mean, it's certainly something we want. It's definitely. I mean, it's one of the reasons we have one of the most recent maintainers of Jython on the project is that we'd like to throw Jython away. So yes, we're definitely interested in that. I don't think anyone's actually really seriously thought about the CLR, because I don't think we have anyone on the project who knows that much about it, but it's certainly it's up there. It's in the idea space. And so what was the second part of your question?
What is the LLVM?
Yes, what is LLVM? LLVM is a low-level virtual machine, is what it stands for. I think you could say it's a kind of portable assembler, basically. Portable assembly language.
What is the current level of test compliancy with the Python 2.4 for PyPy?
Very good, basically. It's something like 90% of the core tests run. I mean, we fail some tests because we miss extension modules, and we don't have weak refs, but pretty much everything else works.
With respect to the global interpreter lock, does that implemented currently in the C backend, or do you have to, or does it crash if you step on yourself in threads, or does it support threads at all?
Yes, I mean, so currently it's one of our options. You can build a PyPy which has support for threads and one which does not. And the only way we support threads at the moment is with a global interpreter lock style model.
And finally, is there any work being done on a transactional memory object space?
Yes.
Or
but there's a guy called Nicholas Riley who's at some university somewhere in the States who's working on that at the moment. I don't know very much about the details of it, but he hangs around the PyPy OSC channel, so you can probably talk to him there.
This is all very interesting, but I'm kind of missing like the just overall gestalt of what it's all about. Like, is the goal here to make Python fast? Is to make it integrate with other languages? Like, what is the overriding goal aside from let's do this thing that's really kind of interesting?
No, there is no particular overriding goal, I don't think. About sort of flexibility and fun and fast. Yeah. Okay, well, thank you for listening.
So it's as fast as Python now? Cool.
I can't wait to see you guys.